going to introduce our final speaker in this session. Our next speaker is from Marvell. Our speaker today is Wilson Snyder, who's a distinguished architect at Marvell in Massachusetts, where he's the primary lead architect of the Octeon TX2, previously Octeon TX1, and the Thunder X1 products as well. He's had lead roles in network processing architecture at Maker Communications, Sun Microsystems, and DEC, the DEC Alpha team. And today he's going to be revealing some new details about Octeon TX2. So I'm excited to hear those new disclosures.
And thank you all for attending. So today, first I have a couple intro slides on DPU, which is a relatively new term. So talk about Marvell's view on that, which I think aligns with the rest of the industries. And then I'd like to disclose our CN98xx chip. Oops, sorry, there we go. Okay. And in addition to disclosing the chips, some of the details we'll be talking about the CPU and cache, virtualization, and then coprocessors on the chip. So first, what do we view as a DPU? Well, not surprisingly, a DPU, of course, has processors on it. We believe it has a large number of relatively high performance processors. Of course, those are connected through a high performance memory subsystem, PCI interfaces, all the things you expect on a typical CPU high quality chip nowadays, and virtualization also. In addition, it has a large number of accelerators attached to it and a large amount of connectivity to the outside world. So this might include PCI interfaces, again, to talk to external devices. It probably includes Ethernet interfaces for networking, and also may include whatever the sort of memory connective of the past or future is, which has changed over time. It was SATA a while ago, and now, of course, a lot of drives are attached, NVMe drives, for example, and there's obviously future interconnects coming. And all of those components are interconnected with some sort of high-speed coprocessors that help achieve the high performance necessary either to talk to the CPUs that are either on this chip or other devices that are attached to the chip either directly or indirectly, for example, through Ethernet. So to that end, Marvell has been shipping over 1 million devices so far to some of the largest hypervisors as DPUs, and in some cases attached, some cases standalone devices. And we're proud to announce our 98xx high-end DPU. So this is the highest performing DPU that Marvell has offered so far. And here's the chip. We are currently, oops, or it disappears in the zoom there, but we are currently providing this in prototype form very soon in volume production. This consists of 36 custom designed ARM v8 licensed cores. These cores have attached to them, of course, L1 caches we'll talk about in a minute, and very large amounts of dedicated L2 and L3 throughout the die, total 21 megabytes of cache. These are attached to the outside world through 20 lanes of 25 gig Ethernet, 36 lanes of PCI Express. DRAM, we have 6 controllers that are DDR4 controllers, USB, other Jelly Bean interfaces. In the middle, in sort of the green color here, we have our accelerators, which if you notice is a very large percentage of the die. This is one thing that makes this different from a dedicated CPU die. This is almost 1/3 of the die area on the chip. We have a network interface controller, deep packet inspection, packet processing, crypto acceleration, regular expression, coprocessors, compression. This chip is in a 14 nanometer process. We started this several years ago. It's about 7.5 billion transistors, and it runs between 80 and 130 or so watts, depending on the particular application. We implemented our own custom cores, again, V8 architecture from ARM based. There's a number of firsts in these cores in this generation. We are the first core with the ARM sample-based profile, and we work with ARM to define this architectural extension. This allows you to tag an instruction flowing down the instruction pipeline so that you can benchmark what's happening with that one particular instruction. So you can get, for example, the latency of that exact instruction, as opposed to overall metrics measured across a large number of instructions or in interrupt-based sampling. We're the first core with the ARM memory partitioning. Again, we work with ARM to define this. This lets you segment the caches and segment the bandwidth between different virtual machines or different applications on those virtual machines to improve your scalability and to prevent one VM, for example, from taking all the resources in a hoggy fashion and neglecting the performance of other applications. We also have the largest TLB, at least that we're aware of, we have over 2,000 entries for each of the CPUs. And this helps large applications that have a lot of TLB pressure. Our core is a relatively aggressive out-of-order pipeline. However, it's not sort of extreme because we would prefer to get more cores in as opposed to have a core that uses 3/4 of the die, for example. So to that end, we are for instruction fetch from a 88 kilobyte instruction cache. We feed to a typical instruction fission and fusion unit, register renaming, and then we have 8 execution pipelines, although we typically issue, we can sustain 3 instructions per cycle all the way through the rest of the pipeline. Also in our execution units, we have full floating point units, and we also have a SIMD unit, so 128-bit SIMD, which lets us do things like deduplication or, for example, some compression in hardware or RAID or any of those in the SIMD unit. As far as we're aware, we're the only people left with a 3-cycle load to use on the D cache. We get that by having our custom design team basically custom design the cache substructures. So most of the CPU is a typical PNR flow, but there are structures in it where we definitely took advantage of our very knowledgeable custom design in our group. The CPUs are then grouped in 6s. So there's a lot of multiples of 3 on this chip. It just kind of worked out that way. So we have 6 CPUs. Those attach to a mid-level cache that is instruction only, and we'll talk about the reasons for that in a minute. And then they also attach to a 3.5 megabyte section of the distributed last level cache. So that cache is multiplied by all the clusters. So you see there's 6 of these clusters. Again, each of the clusters getting 6 CPUs. So that gets us to the 36 CPUs. On the left and right of the clusters, we have our 3 on the left and 3 on the right DRAM controllers. And then on the top, we have I/O bridges, which then attach to all of our coprocessors, PCI, and all interfaces to the outside world. One of the other unique aspects of the Octeon architecture is we do have write-through caches. So our L1 D cache within the CPUs is right through all the way to the last level cache, and we design our cache bandwidth to take that into account. The reason we do that is that gives us much better scalability. So if you have applications that have true data sharing between the cores, the lock behavior and data sharing behavior is much lower latency by having a write through because you don't need to transfer the cache line between the L1 caches. When we were designing our mesh, we had a sort of the obvious question, which is how big do you make it? And I think this is interesting to those CPU architects on the phone here. What we did is we looked at the analysis of a lot of the SPECINT benchmarks, and in addition, some benchmarks that aren't shown here that aren't part of SPECINT, SPECFP. And what we determined is that in many cases, the scalability, in other words, the ratio versus perfect scaling of those benchmarks when we added it to the entire chip correlates very, very strongly to the bisection bandwidth available to that particular application across the entire die. So looking at this, and again, other applications, we decided to settle on a 512-bit wide mesh interconnect. And this gives us over a terabyte per second of cross-section bandwidth within the die. Also, if you look at the slideshow, the previous things, if you happen to review it online, we actually route these wires over the top of the cache. So our caches, for some extent, are free because we have the wires anyways running over the section of the die. One of the other things that guided our design of the core architecture was being able to run large footprint applications. So for example, the Linux networking stack and Nginx, which is a web server application, and a bunch of other networking and storage applications. When we did this, we found that if we took our new higher performing core, what was supposed to be a higher performing core and also faster clocked core, we were not getting significant IPC speedups. And the reason is what was happening is basically the iCache was always missing. So it was just too small to hold the large programs we wanted to be able to run. So the logical thing to do would be to throw down an L2 cache, which is shared between I and D, which is what a lot of processors have. Unfortunately, because of these applications are also moving a large amount of data, the D stream data would throw the data out of the iCache. So we decided to do an instruction-only mid-level cache, and we find that that performs extremely well for applications with very large footprints. And when we do that, we have some applications that are showing more than a 2.4x improvement by having that mid-level cache. And again, it's instruction-only, which is a little unusual. This is our 3rd generation product, which has very aggressive virtualization in our coprocessor in addition to our cores. We made a number of improvements in this generation. We had previously had a relatively static division of resources. Software could decide how to assign things, but it had no control over what was in a virtual function or a physical function. We now have an ability for hardware to have the concept of what we call logical functions, or LFs. These are physical divisions of the hardware. So this is the way the hardware actually operates, is on divisions called logical functions. But software can then assign these logical functions between physical functions and virtual functions however it wants. So if software wants to make a given virtual function that's perfect for DPDK use, it can do so. If it wants to make another kind of virtual function or physical function that's perfect for the Linux networking stack because it includes, for example, only a NIC, it can do that. If it wants to make a virtual function that's only for cryptography because it wants to talk to OpenSSL, it can also do that. So this gives us a lot of flexibility and a lot better reuse of the hardware and a lot better software compatibility. And all the support for this has already been upstream to the Linux kernel and is supported by all the standard both hypervisors and operating systems out there. This shows our general packet flow, through the chip. And this is just focusing on networking. Obviously, you can move data in other ways, including through PCIe. But for simplicity, we'll just talk about Ethernet connectivity. So a packet comes in the Ethernet interface up on the upper left. It enters our packet receive block. We have flexible packet processors that can process the headers, extract certain fields from those headers, make a decision what the flow is about, and decide whether to admit the packet or not. This also decides which of the 128 virtual functions the particular packet's going to go to, and on that particular virtual function, which of over 1 million receive queues within that virtual function it's going to get shipped to. The packet would then either go to memory, or also we support inline IPsec, so we can take the packet, we can automatically decrypt it, and put the decrypted data into memory. So when the CPU gets it, it's all decrypted. It's almost as if it never had to be decrypted in the first place. So that offloads the CPUs. There's 2 different models for delivery to software. One is the traditional ring-based NIC model. The other is we have an event-driven hardware accelerator block called our SSO block. And this is a hardware scheduler we'll talk about in a minute that allows event-based processing for much better performance for some applications. We have a hardware buffer manager that is like malloc and delete, basically, where we can handle the allocation of buffers in memory. And then on the egress side, when the CPUs want to send a packet, they can do a send command to our hardware packet transmission block. That send command has special hardware behind it. It does not require a lock. It doesn't require the CPU to add anything to a queue. It's all handled by hardware. This allows multiple CPUs to send a packet to the same exact queue, and the hardware will maintain the ordering without any locks in software. So this greatly helps scalability by removing locks from what would otherwise be critical sections of the code. In that egress block, we have, again, 1 million queues, 128 virtual functions, and we have a 5-level shaper and scheduler 2-color shaper topology. So you can have very complex workloads. So for example, you can have a particular queue that's limited relative to other queues or higher priority relative to other queues. And all this can be shaped down to, for example, 100 gigabit lane. The egress packet then goes back to our packet processor, where we can analyze the particular headers in the packet, and we can optionally replicate it or mirror it, handle ARP packets, either send it back through the network or send it out one of our Ethernet interfaces or send it out PCI. Just like on inbound, we also have crypto on the transmit direction, inbound crypto. So again, if the core wants to send a packet that's going to be encrypted, it can just write the unencrypted data to this coprocessor, just like as if it was never going to be encrypted. The hardware will encrypt it, enqueue it, and then transmit it without the CPU having to be involved in the encryption flow. Our crypto hardware is about our 6th or 7th generation. Our GigaCipher encryption engines, which are microcode-based engines. These support both the standard symmetric algorithms up to over 200 gigabits of crypto on this part. And these also support asymmetric algorithms, both elliptic and standard RSA, et cetera, and hashing also. And this supports almost 100,000 RSA operations per second, which is a very high rate of RSA operations. This device is fully virtualized like all the others, and we have special hardware again for inline IPsec, and also for the cores to offload OpenSSL or other standard crypto libraries, or your own crypto if you wanted. We have a hardware scheduler, and again, the typical use of this is event mode DPDK. Which is one of the libraries in DPDK, among others, that Marvell has contributed to the community and worked with the community to define as a standard. The purpose of this block is basically let's say you're getting a bunch of packets, and these are represented by colors on the right-hand side. Some of the packets are to the same flow, that is generally between the same source and destination. We support unordered mode, where any of the particular packets can be assigned to any of the 3 cores shown here stacked vertically. We support something called ordered mode, where the hardware will keep track of what orders the packets came in, and what allows us to run the same flow on 3 different cores, and the hardware will remember the ordering. Therefore, we can establish parallelism and use all 3 cores in parallel on the same flow, which is something that is otherwise very hard without this dedicated hardware. Or finally, we have what's called atomic, which is a case where a given flow can only execute on a given CPU. So it cannot be executed by multiple CPUs in parallel. And again, we have special support in our architecture, and also even all the way down to the CPUs. So some of the interactions with this block actually are only 3-cycle operations. So it's extremely fast to interact with this hardware. The purpose of this block is demonstrated by this slide. So what we have here is on the left-hand side, we have varying packet sizes. And we have what happens if, let's say you start with 1,000 flows, which is the higher bar there. You're getting great application performance. You're happy with the product. And then someone says, well, what happens if I get an elephant flow? I get a flow which is basically consuming all the bandwidth, and I only have one of those flows. Well, basically, your performance just drops way off. And this tends to make the end customers very unhappy. It's like, what's going on? My performance dies when I get this big flow. So that's the reason we have this hardware block. On the right-hand side, you have what happens if you switch to event-driven DPDK using our scheduler block. What happens is you do get slightly lower performance, admittedly, when you use the block versus software, because there is some more instructions required. However, if you notice, the drop-off in performance between the 1K flow and the 1 flow case is very, very small. So by taking a very small penalty in the best case, you get a huge upside on the worst case. So basically, your tail latency is significantly better. So most of the customers we work with, totally understand this, and they find that an excellent trade-off, to lose a very small percentage of performance in your best case to get absolute common behavior regardless of the number of flows in the system. This is our 3rd generation of chips that has a regular expression coprocessor in it. We've redone much of the hardware and worked with a number of our customers to improve this hardware. There are 2 units. Each of them can handle 50 gigabit stream of data, and it can match this against potentially millions of rules. The typical use of this is for firewall acceleration. So for example, what you want to do is you want to look against virus signatures to say, is this particular email or packet traffic match something that has a signature of a virus against it? So this hardware will do that. It does that through having 64 engines, which is, again, fully virtualized, and again, can process a total of around 100 gigabits per second of network traffic, looking across those million regular expressions to determine if any of these packets match a virus or what have you want to represent. In the end, what we've delivered is roughly a little bit above a 350 SPECINT machine. This gives us, almost a 50% improvement over our previous part, which was the CN96xx, which had 24 cores. So, pretty good scalability there, about what we aim for. And this delivers over a factor of 3.5 over our previous generation, which the highest end in that case was the CN98xx, which was a 24-core part. So you see that, over these last 3 parts, we had almost a doubling, even though the same core count, by adding much better out of order, adding much better cores, and then increasing the core count again, we got a good factor of 50%. So pretty good improvements over the generations there. And then there's some other competitors there. You can sort of get a picture of where we are relative to them. So thank you for your time, and look forward to your questions.
Okay, thanks, Wilson. I think we've got a few audience questions. And I appreciate you diving into some new detail there. Go ahead and turn off your screen sharing so everybody can see you. And I think if I have my numbers right here on Octeon TX generations, is your mesh now 4 times the width that it was in your previous generation?
Our previous generation wasn't really a true mesh, but that's roughly, if you sort of could do a bisection bandwidth, that's roughly correct.
Mm-hmm. Okay, I think I was looking at one of our articles, I thought it was 128 bits wide, but I guess it was a little bit different architecture.
Yeah, it was 128 bits, but it wasn't a XY kind of mesh. It was sort of more of a spidery thing, so it's not exactly equivalent, but pretty close.
Okay, and then ThunderX2, I believe, uses bidirectional rings instead of a mesh. Is that right?
That's correct. Yeah. So
how would you sort of compare and contrast the two, and why you went with the mesh on the Octeon side?
Yeah, so we did some analysis of rings. I think really the difference comes down to what size parts you want to build. So this particular mesh architecture, we needed something that could go all the way down to a single 6-core implementation. It could also go up to even potentially a little beyond 36 if we wanted to build it. And when we looked at where the ring was in terms of some of the trade-offs with some of the sizes we wanted to be able to build, it didn't really fit. So I think you really need to choose from a sort of product generation, looking across the entire generation of a product where you want to land.
Okay, so it's really a kind of a scaling issue.
Right.
Yep. Okay. I've got a bunch of questions, but I know there's some audience questions as well. So I'm going to work through some of those, and we'll see how much time we have here. Question about die area. Not sure if you're able to reveal the die area of the device.
No, I'll say the reticle's nowhere in sight, so I will leave it at that.
Okay, fair enough. Next question is regarding the what the attendee views as unconventional sizes for the I cache and D cache.
Yeah, we add those just to make sure people are paying attention. Because if you don't notice those weird powers of 2, then you're probably not paying attention to the presentation. Yeah, so we have basically a custom design heritage. So our opinion of caches is you pack as much as you can in for free. There's some minimum size, of course, but for the most part, you keep packing in until either your cycle time breaks or you run out of area. So for both our I cache, D caches, and L2 cache and L3 cache, for all of those, basically we kept cramming until we either hit the cycle time wall or we ran out of area. In most cases, I think we ran out of area. Actually, I think all of the cases we ended up running out of area before we hit the cycle time.
Okay. There were a couple questions on IPsec performance, which I think you answered in subsequent slides, but I think there's one related question I have, which is, when you're talking about the packet flow, there's always kind of this knock on devices like Octeon that the ARM CPU has to touch every packet. So I think the related question on IPsec was, how many CPU cycles are you burning to do the kind of IPsec throughputs you were talking about?
Well, so previous generations, the CPU had to sort of have high touch, let's say, of every packet. Now it's sort of more administrative touch, so to speak. There are a couple of cores to get those data rates, but it's in the couple of core range. It's kind of, the mileage varies a lot, so I don't want to give an exact number, but it's in the couple of core range. So on a 36 core part, it's a small fraction of the total available.
Okay, great, thank you. Another question was regarding IPC and how this core compares to like a Cortex A72 or your Vulkan CPU.
Yeah, so it's certainly well below a Vulkan, which is a much larger core. Vulkan is on the order of the area of 3 of these cores, which is the reason we chose not to use that particular core. This is higher performing than an A72, and our area and power efficiency is better than an A72. So in the same technology. So we got, and this was designed actually, and I think we started a little bit before A72 was available too. So from a power area and that standpoint, it's a little better than A72.
Okay, I think you just answered the next question, which was, why would you use a custom core instead of ARM's Neoverse? Yours is better.
Well, I mean, every generation, I mean, not that we don't like doing CPUs, but every generation we look at everything that's out there and we make the appropriate choice, and that's what, our job is not to build custom cores. Our job is to deliver a product that works. And every generation we look at what's out there and we make what we think is the best choice. And for this particular generation, I think building our own was the right choice.
Yeah, I mean, I know there's some of the lower end products that are now Octeon branded that use off-the-shelf ARM cores.
Yeah, we certainly have many Marvell products that use off-the-shelf cores. Yeah.
Okay, question, any RAS features in this device?
Oh, yes, I didn't talk to that, but absolutely, yeah. So we have, of course, ECC on the external DRAM and all throughout the large cache subsystems. We have a very low fits rate overall. We also were one of the first chips to go with the ARM, has a new RAS standard. So we helped them with that, and the chip implements those RAS features. And we also have a system control processor, which is a dedicated MPU that basically is in charge of dealing with power and RAS. Okay,
great, thanks. I wanted to come back to the cache hierarchy because I think that's pretty interesting. And as far as I know, the kind of instruction-only L2 is unique in everything I've seen. So in this new cache hierarchy, your shared L3 kind of serves as the equivalent of the L2 data cache. Is that right?
Effectively, I would think of it as data just goes L1 and there is no, it just goes L1 all the way to L3. And then instructions go L1, L2, L3.
But I guess from a latency perspective, how does that compare to having kind of the L2D versus just going straight to the L3?
Well, it depends what your L1D architecture is. So if your goal is best single-threaded performance, in most cases, and mileage varies, right? But in most cases, I think you're better off with a dedicated L2 cache. But that isn't our market. Our market is generally applications where there's a large amount of data sharing. And if you have dedicated L2 caches, there is a cost in sharing locks between, or any data between cores between those L2 caches. So you gain from single-threaded performance, but you tend to get a much worse behavior for scalability when you go to multi-core. So because this part, again, is aimed at multi-core, that's sort of what drove us at both having that large L1 cache, but also getting the data as soon as possible from a store inside a CPU to where every single CPU can see it. And that both meant we didn't really want a per CPU L2, and it also meant that if we had had a large L2 in the middle, like we could have easily had an L2, one L2 that was data, one L2 that was I, that would have been a choice. And we did model that. But we decided not to because, again, the problem we then saw is that when we have data sharing, it would have hurt our scalability with a large number of cores.
Yep. Great, thank you. Very interesting, application-focused approach. So a couple more audience questions here. Do you support 200 gig Ethernet max in the device?
The maximum single MAC we support is 100 gig, so it'd be 4 by 25.
Okay. And then we talked a little bit about the core performance, but an attendee is asking for performance relative to x86. So how would you characterize it relative to some of the devices you were showing in that performance graph?
Well, it totally depends on which x86. We're better than some and not as good as others. And again, it kind of comes down to performance relative to power. If you graph it relative to power and cost, we'll pretty much beat them across the board. If you pick just performance, of course, there's x86s that perform much better, but you're paying for it with something, right? So if you have more specific questions, we can talk to it. It'd probably be better if we can just talk in the breakout.
Yeah, I noticed you had Skylake D on your chart there. I'm curious whether you've looked at Snow Ridge because that's kind of an in-between. It's got the new Tremont CPU.
Yeah.
And where you think you sit relative to that device?
I think we look okay. I don't remember the numbers off the top of my head, so I won't get myself in trouble.
Okay. But I think conceptually, maybe it's kind of along the same lines from finding that sweet spot in power and performance. Okay, we are actually out of time, and so Wilson, thank you very much.